We'll be covering torque and angular momentum. What is torque? What is angular momentum? How to calculate them? What is the relation between them? Then we'll be moving on to moment of inertia, how we calculate moment of inertia, what it signifies, then the theorems, perpendicular axis theorem, parallel axis theorem, how we apply them. Then we'll be doing to radius of gyration, moment of inertia of some fixed rigid bodies and composite systems. Okay. After that, we'll be covering rotating rigid body, that if we have a rigid body which is rotating with some angular speed omega, then what will be its torque, what will be its angular momentum, what will be its kinetic energy. So the dynamics of a rotating rigid body. After that, we'll be doing rolling motion. Okay, so without wasting any time, let's start our recap session. The first topic is torque. So what is torque? Now see, can we open the door by applying force anywhere? Just apply the force on the hinge. Can you open it? No, we cannot open it. Can we open the door by applying a force parallel to the plane of door? No, we cannot open it. So why we can open the door only if we apply the force at some distance from the axis about which it is rotating, or at some distance from the hinge, and the force must act perpendicular if we want to rotate it easily, or we can say that force must act any angle theta with the plane of the door. So this is determined by torque. So what is torque? The rotating effect of any force is called torque. Okay, so what is torque? It is the turning effect. Turning effect of any force is called torque. Now how we define torque? Torque is defined as the cross product or vector product of position vector and force vector. Okay, it is the vector product of position vector and the force vector. So torque is denoted by tau. It is defined as R cross F. Okay, torque is defined as R cross F. Now see, if we define torque as R cross F, how we define it? Suppose we have a rigid body, it is rotating about this axis, and a force F is acting at some distance from the axis of rotation. Okay, now this vector drawn from the axis of rotation to the point where force is applied is called the R vector. Now there must be some angle between the two. Angle between them is theta. Okay, angle between them is theta. So we define torque as R cross F. So torque magnitude is equal to R into F into sine theta. Okay, magnitude of torque is R into F into sine theta. Now if the force has a tendency to rotate the body anti-clockwise, then a torque is taken as positive, and if the tendency of the force to rotate the body is clockwise direction, then it is taken as negative. Okay, just like we have in this case, the body will rotate like this in the anti-clockwise direction, so torque will be taken as negative. Now if theta is 0, theta is the angle between R and F. So if theta is 0, then torque will be 0. If theta is 90 degree, then torque will be simply R into F, and this is the maximum torque which can act. Okay, now see, torque is R into F if it is the maximum torque, because sine theta can have the maximum value of +1 when theta is 90, sine theta is 1. So maximum torque acting on the body is Rf. Now it is a vector quantity. It is a vector quantity. Its SI unit. See from this, it is the product of Rf sine theta. Sine theta is dimensionless, so its SI unit is Newton meter, and its dimensions dimensions will be ml2t minus 2. Okay. Now how to calculate the torque? Suppose we have this rigid body which is rotating about this axis. Okay. And a force F is acting like this. So draw the position vector from the axis of rotation to the force. We will get the R vector. Angle between them is theta. So there are two ways by which we can calculate torque. If we resolve F into two components, we will get F cos theta and F sin theta. Okay, we will get two components, F cos theta and F sin theta. Now F cos theta is parallel to R. Torque due to F cos theta will be 0. F sin theta, can we call it F perpendicular? Because it is perpendicular to R vector. The component of force which is perpendicular to R, we call it as F perpendicular. Now see, torque will be R into F into sin theta. So simply torque is R into F perpendicular. This is one way of calculating torque. That how can we calculate torque? We can calculate torque by resolving F into two components, one parallel to the R vector, this is F parallel, and this will be F perpendicular. Okay, one component perpendicular to R vector and one parallel. So torque is simply R into F perpendicular. Another way of calculating torque is instead, if this is my rigid body, let us draw it. Okay, let us take this any arbitrary rigid body. It is rotating about this axis. Okay, it is rotating about this axis. Now this is my force acting at this point. How we draw R? This will be my R vector from axis of rotation to point where force is applied. This will be angle theta. Now the second method says that draw the line of action of force. Okay, extend the line of action of force like this. Now draw a perpendicular from the axis of rotation on the line of action of force. Okay, draw a perpendicular from the axis of rotation on the line of action of force. If this angle is theta, this will also be theta. Okay, this is our hypotenuse, this is angle is 90 degree, so this will be R sin theta. Okay, this distance will be R sin theta. Let us call it R perpendicular. Okay, let us call it R perpendicular. Perpendicular distance on the line of action of force is called R perpendicular. Now can we write torque as R sin theta into F? Torque is RF sin theta. So we just rearranged the terms. So torque is equal to R perpendicular into F. Okay, so there are two ways to calculate the torque. First way is resolve F, find F perpendicular, the component perpendicular to R. Next way is draw the line of action of force, draw a perpendicular from the point of rotation, axis of rotation on the line of action of force. That is called R perpendicular. So torque will be simply R perpendicular into F. Now if we have R vector defined as Rx I cap plus Ry j cap plus Rz k cap. Okay, and F vector is defined as Fx I cap, Fy j cap and Fz k cap. Okay, these are my R vector and F vector defined in Cartesian coordinate system. Then what will be my torque? torque is R cross F. How we calculate cross product of two vectors? We calculate cross product of two vectors by determinant rule. So write I, J, K, then R. First vector is R, so write the component of R first. Rx, Ry, Rz. Then write the component of force Fx, Fy, Fz. Okay. So this will be my R cross F. Now expand it. Simply write plus minus plus. So this will be equal to I cap into Ry Fz minus Fy Rz. Then minus J cap Rx Fz minus Fx Rz plus K cap into Rx Fy minus Fx Ry. Okay. So this is how we calculate torque in rectangular components. This is all about torque. Let's move to angular momentum. Let's move to rotational equilibrium. Okay, rotational equilibrium. Now, as we have studied translational equilibrium. When is translational equilibrium? When net force on the particle is 0. Either the particle will be at rest or it will be moving with constant velocity. Okay. Now, when it is net torque on the particle 0, okay, net torque on the particle is 0, it means either the particle or system or the body will be at rest or it will be rotating with constant angular velocity, then torque on it will be 0. So, when the sum of clockwise torque and anti-clockwise torque, okay, when the sum of anti-clockwise movements about any point is equal to the sum of clockwise movements about that point, then we can say that the body is in rotational equilibrium at that point. Okay, so let us consider a system of a lever system. We have a fulcrum and a force F1, or let us apply it downwards if you are keeping mass. F1 is applied at this end and it is a distance of R1 from the fulcrum, and at R2 distance from the fulcrum we have applied a force F2. Now F2 has a tendency to rotate the clockwise and F1 has a tendency to rotate it anti-clockwise. When there is situation of equilibrium, net torque will be 0. Okay, net torque about any point will be 0. So calculate the torque. Anti-clockwise torque is equal to clockwise torque. So we will have F1 into R1 will be equal to F2 into R2. So from here we will have F1 by F2 is equal to R2 by R1. Okay. So this is, we can say that if you want to lift any heavy mass, then apply a force or the force are in the inverse ratio of distances. So more the force, lesser will be the distance. Okay. So this is rotational equilibrium when the sum of movements about any point is 0, or we can say that clockwise torque is equal to anti-clockwise torque. Net torque about any point is 0, then the body is said to be in rotational equilibrium. Now see the next topic, couple of force. What is a couple of force? If you have a rigid body, okay, if you have a rigid body, on this rigid body, one force F1 is acting in this direction and other force just equal and opposite. Let us take F and F. Okay, one force F is acting at this point in this direction, other force F is acting at this point in this direction. Okay, now they are equal in magnitude and opposite in direction. Also the line of actions of the two force, draw the lines of action. The line of action of two force are separated by some distance d, then this two forces constitute a couple of force. Okay, two equal and opposite forces acting on a body along two different lines of action constitute a couple. Okay, they constitute a couple. Now if you want to calculate torque about any point, let us say about this O point, okay, then torque due to a couple of force is, this is equal to, torque will be equal to magnitude of force into magnitude of force into perpendicular distance between the lines of action of two forces. Okay, this is how we calculate torque due to a couple. So torque due to a couple, tau is equal to F into D. Okay, torque is equal to F into D. This is the torque due to a couple of force. Magnitude of any force, because they are equal and opposite, equal in magnitude, multiplied by the perpendicular distance between the line of action of the two forces. This gives us a torque due to a couple. Work done by a torque. How much work is being done by a torque? Whenever we apply a force, body displaces. Work is said to be done. Similarly, we applied a force, body rotates, then torque is acting due to that force. What is the work done by the torque? Okay, suppose we have a body which is rotating about this axis. We applied any force F, okay, and a torque will be acting. Okay, so this body is rotating under the action of the force tau. So work done by torque in rotating, or let us say work done by torque is equal to torque into displacement. Okay, it will be tau into theta 2 minus theta 1. Okay, it is torque into angular displacement. Just like force into linear displacement, then work done by torque is torque into angular displacement if my torque is constant. Okay, if tau is constant, and if torque is variable, then how we define it? Work done by torque is equal to integration of tau d theta from theta 1 to theta 2. Okay, this is how we define work done by torque when torque is variable. Similarly, if you want to find power delivered by torque, then it will be tau dot omega. Okay, power delivered by torque will be the dot product of tau dot omega. You can easily obtain this expression if you just differentiate it, okay, once, then we will get this expression. Okay, now let us come to angular momentum. What is angular momentum? Just like the rotational or turning effect of a force is called torque, similarly the rotational effects, or how much rotational motion is contained in a body, okay, how much rotational motion is contained in a body is given by angular momentum. Okay, so angular momentum of a particle rotating about an axis is defined as the movement of the linear momentum of the particle about that axis. Okay, it is the movement of the linear momentum. How it is defined? It is defined as the vector product of position vector of the particle and the linear momentum of the particle. Okay, vector product of position vector and linear momentum. So let us say a particle is rotating about this axis of rotation. Okay, then the particle is having linear momentum P in this direction. It is having velocity. Now draw it, position vector from the axis of rotation. This angle will be theta. So position vector from the axis of rotation. Now if we say that it is rotating in a plane, let us say that it is rotating. We have a particle of mass m rotating in a plane about this axis. Okay, about this axis of rotation passing through the plane. So this is the momentum of the particle, this is the position vector from the axis of rotation to the particle. Okay, this gives us the r cross angular momentum. Sorry, I have written tau, it will be L. Angular momentum is denoted by capital L. So L is the moment of linear momentum. L is defined as the vector product of r cross P. Okay, if we define L magnitude, it will be rp into sine theta. Okay, it is r cross P in vector form and rp sine theta. Now cross r cross P, it will along the axis. Torque and angular momentum are axial vectors. They act along the axis of rotation. So this is rp. Now if theta is 0, then angular momentum will be 0. And if theta is equal to 90 degree, then angular momentum is simply rp, and this is the maximum value. Okay, this is the maximum value of the angular momentum it can have. Similarly, write its SI units. So SI units will be, angular momentum is r into p. R is meter, p is kg meter per second. So it will be kg meter square per second. Dimensions, it will have the dimensions ml2 t minus 1. Okay, it is also a vector quantity. It is an axial vector. Okay, acts along the axis of rotation. Okay, acts along the axis of rotation. Now see, if you have r vector is equal to rx I cap plus ry j cap plus rz k cap, and linear momentum as px I cap plus py j cap plus pz k cap, then what will be my angular momentum? Angular momentum is r cross p. So it will be simply the cross product of the two vectors I, j, k. Write components of r first, rx, ry, rz, and the components of p, px, py, and pz. Now open this determinant or expand it about I, j, k axis, then we will get the L vector. Okay. Now similarly, just like how we calculated the linear torque, suppose if we have, this is my plane and we have this as the axis of rotation, this is a particle of mass m. Okay, it is having linear momentum p in this direction. Then from the axis of rotation, this will be my r vector. Angle between the two is theta. Okay, so you can do two things. Either you can resolve p vector, or you can draw the perpendicular from the axis of rotation onto the line of action of the momentum, linear momentum. You can call this r perpendicular. Now this angle is theta, this angle will also be theta. So r perpendicular will be equal to r sine theta. So we can write angular momentum as r sine theta into p. So simply it will be r perpendicular into p. Okay, so draw the line of action of linear momentum, Draw the perpendicular from the axis of rotation onto the line of action of linear momentum. Multiply the two, you will get the angular momentum. Or in other way, what we can do is we can resolve P. This was the P. Let us do it over here only. We can resolve P into two components. This will be P cos theta and this will be P sin theta. So P sin theta is called P perpendicular. Now P cos theta will yield no angular momentum. So when we solve it, we can write angular momentum as R into P sin theta. P sin theta is P perpendicular. So we can write it as R into P perpendicular. Okay. Both ways for determining the angular momentum are correct. Okay. Now as we have studied angular momentum and torque, what is the relation between the two? Okay. What is the relation between the two? Now see, angular momentum is equal to R cross P vector. Now calculate dl by dt. Differentiate it, you will get dr by dt cross P and you will get R cross dP by dt. Okay. Now dr by dt is V and linear momentum is mv plus R into dP by dt is F. Cross product of two similar vectors. There will be zero angle between P and V. Okay. P is just mv. V cross V will yield 0. So this will be null vector plus R cross F. So from here R cross F is tau. So we will get that dl by dt is equal to R cross F. Okay. Or it is equal to tau vector. This is the very important relation, that torque is equal to dl by dt. Rate of change of angular momentum yields torque. Okay. Now if we have torque to be 0, okay, if tau net is 0, then we will have dl by dt is 0. So dl by dt vector is a null vector, then L must be a constant. Okay. L must be a constant vector. So this is the law of conservation of angular momentum. Okay. Law of conservation of angular momentum. Okay. This is the law of conservation of angular momentum. Now let us come to moment of inertia. Just like we have studied in translational motion that inertia is the property of any body to maintain its state, or inability of any body that it cannot change its state by its own self, that is the inertia. Similarly, in rotational motion also, every body tends to maintain its rotational state of motion, or it has the inability that it cannot change its rotational state of motion by itself. This property of the body is called movement. This body is called in rotational inertia. Now, as mass was indicating that how much translational inertia body will have, similarly we have a quantity which is analogous to mass in rotational motion, translational motion. Okay, that is moment of inertia. Moment of inertia will tell us which body is having how much ability to maintain its state of rotational motion. More the moment of inertia, more will be its rotational inertia, or we can say that it has more tendency to maintain its state of rotational motion, or it can inability to change its state by itself. Okay. Just like if a body is having more inertia, we need more force to change its state. If a body is having more moment of inertia, we need more torque to change its state. Okay. So what mass is doing in translational motion will be the same as moment of inertia in the rotational motion. Okay, so let us study what is moment of inertia. Moment of inertia of a rigid body about a fixed axis. So here comes the first important point, that moment of inertia is always defined by defined about any axis. Okay, we cannot define it arbitrarily, it is always defined about any axis. So first define the axis about which you want to define the moment of inertia. So moment of inertia of a rigid body about a fixed axis is defined as the sum of the products of masses of the particles constituting the body and the squares of their respective distances from the axis of rotation. Okay, so if we have a rigid body and it is rotating about this axis, so all the particles are also rotating. Let us assume that it is made up of n number of particles, m1, m2. m1 is at a distance r1, m2 is at a distance r2. Similarly, mn is at a distance rn. So from here we will define moment of inertia. I will be equal to m1 r1 square plus m2 r2 square up till so on mn rn square. Okay, this is how we define moment of inertia, products of the masses of the body and the square of their respective perpendicular distances from the axis of rotation. Okay, so if you want to sum it in the form of summation, we can write it as mi ri square, where I goes from 1 to n. This is how we define moment of inertia. Okay, this is for discrete mass system. For continuous mass system, we will consider a small mass dm. Okay, so if we have for continuous mass distribution, okay, so for continuous mass distribution, I will be dm into r square. Okay, so we will consider an elemental mass dm which is at a distance r from the axis of rotation. So this summation will turn into integration. It will be simply I is equal to dm into r square. This is how we define moment of inertia. Now moment of inertia is a tensor quantity. Okay, its SI unit will be mass into distance square, kg meter square. Okay, this will be its SI unit. So this is how we define. Now let us define the moment of inertia for some fixed rigid bodies. Like if we have a rod, then moment of inertia about an axis passing perpendicular to the rod. This axis, this is a rod of mass m and length l. It will be ml square by 12. If we have a ring, okay, if we have a ring, then its moment of inertia about its own geometrical axis, I is equal to mr square, where m is the mass of the ring and r is its radius. Similarly, if we have disk of mass m and radius r, then its moment of inertia about its geometrical axis is mr square by 2. All these moment of inertia we can calculate using the integration method. Okay, if we have a solid sphere, then its moment of inertia about its diameter about this axis, it is 2 by 5 mr square, where m is my mass and r is its radius. Similarly, if you have hollow sphere, okay, its moment of inertia about this axis will be 2 by 3 mr square. Now there is a complete list of such rigid bodies, uniform rigid bodies. You can remember all this list. Okay, let us move forward to the theorems of moment of inertia. What parallel axis theorem says that? See, parallel axis theorem says that if you have any arbitrary rigid body and you want to find moment of inertia of this body about this axis, first what you need is draw a parallel axis passing through center of mass. Okay, draw a parallel axis passing through center of mass of the body such that perpendicular distance between the two axes is d. Okay, such that perpendicular distance between the two axes is d. Then moment of inertia of this rigid body about this axis is I, and about this axis is right ICOM. Okay, now it is easier to calculate moment of inertia about the center of mass axis, or in general for rigid bodies we know that what is the moment of inertia about center of mass axis. Okay, so we can calculate it about any other axis. This theorem says that the moment of inertia of any axis about any axis is equal to sum of moment of inertia about an parallel axis passing through center of mass plus mass into distance between the two axes whole square. Okay, so this is parallel axis theorem. Moment of inertia of any rigid body about any axis is equal to its moment of inertia about center parallel axis passing through center of mass. Okay, parallel axis passing through center of mass. Axis should be parallel and passing through center of mass plus the product of the mass of the body and square of the perpendicular distance between the two parallel axes. Okay, if you want to find moment of inertia about this axis, then draw parallel axis passing through center of mass, find the moment of inertia about that axis, then I will be ICOM plus MD square. Let us move to parallel axis theorem. Now parallel axis theorem is only and only applicable to laminar bodies. Okay, only and only applicable to 2D surfaces. Okay, 2D bodies. Now they are saying that if you have any rigid body in a plane, okay, if you are having any rigid body in a plane like this, let us consider this as x, y and z. Okay, or let us consider better it to be simple system of x, y and z. Now this is a laminar body lying in the xy plane. Okay, this is a laminar body lying in the xy plane. Now this theorem says that the moment of inertia of a body about an axis perpendicular to the plane. Okay, moment of inertia of a body about an axis perpendicular to the plane of the body is equal to the sum of moment of inertia of the body about two mutually perpendicular axes lying in the plane. Okay, so Iz will be equal to Ix plus Iy. That if you want to find the moment of inertia of this body about axis perpendicular to the plane, you have to find two mutually perpendicular axes which are lying in the plane. So the sum of the Ix plus Iy will give you Iz. Okay, so moment of inertia of any axis about any lamina about any axis perpendicular to the plane is equal to the sum of the moment of inertia of the lamina about any two mutually perpendicular axes lying in the plane, and all these three must intersect each other at the point where this perpendicular axis is passing. Okay, where this perpendicular axis passes through the lamina. You cannot take these mutually perpendicular axes over here. You have to take them from the point they must intersect at the point where the perpendicular axis is passing through the lamina. So Iz will be equal to Ix plus Iy. This is perpendicular axis theorem and only applicable to laminar bodies. Let us see what is radius of gyration. The radius of gyration of a body. Okay. Now this is, suppose we have a complete rigid body. We find out the moment of inertia of this body about this axis. Okay, we found out that moment of inertia of this body about this axis is I. Now if we concentrate whole mass of this body at some point, if we concentrate whole mass of this body at some point, then the distance from the axis of rotation where this point mass should be placed such that moment of inertia of this point mass is same as the moment of inertia of this complete mass distributed rigid body about this axis. Okay, if the whole mass of the rigid body is concentrated at a point, then where we should place this point mass so that moment of inertia, if we calculate it over the whole distribution of this rigid body, it is same as the moment of inertia of this point mass. Okay, so K will be our radius of gyration. Radius of gyration of a body about its axis of rotation. Just like moment of inertia, it is also defined about n axis of rotation, can be defined as the distance from the axis of rotation. Distance from the axis of rotation at which if whole mass of the body were supposed to be concentrated, then its moment of inertia about the given axis would be the same as with the complete mass distribution. Okay, so both the cases moment of inertia will be same. Now if you want to find moment of inertia, so first case moment of inertia will be equal to moment of inertia in this case. So it will be equal to moment of inertia of this particle will be m at a distance k. Moment of inertia will be m k square. I will be equal to m k square. Now if it is made up of masses of mass m1 at distance r1, m2 at distance r2, similarly mn at distance rn, then we will have m1 r1 square plus m2 r2 square up till so on plus mn rn square will be equal to mk square. Okay, so from here we will get k is equal to under root of m1 r1 square plus m2 r2 square up till so on mn rn square divided by mass of the whole body. Okay, divided by mass of the whole body. This will be our radius of gyration. Okay, this is the radius of gyration. Now let us come to dynamics of a rotating body. Suppose if we have a body which is rotating with angular acceleration alpha. Okay, suppose if we have a body which is rotating with angular acceleration alpha and about this axis, and moment of inertia is I about this axis. Okay, then torque acting on the body, then torque acting on the body is given by torque is equal to I into alpha. Okay, torque is equal to I into alpha. Similarly, if you have a rigid body which is rotating with angular speed omega, okay, or at any point of time its angular speed is omega. Okay, now it is accelerating, its angular speed is omega at any point of time. So angular momentum of the body, angular momentum of the body is L will be equal to I omega. Okay, torque of the body is I alpha, angular momentum is I omega. Now kinetic energy of the body, so rotational kinetic energy, rotational kinetic energy is given by half I omega square. Okay, these are the rotational parameters. You can derive them very easily, they are very easy to derive. So Ke rotational, okay, or we can say that Ke rotational is equal to half I omega square. So Ke rotational is equal to half I omega square. This is a very important relation, that rotational kinetic energy is half I omega square. Now we know that L vector is equal to I omega. So from here we can write L by I, omega is L by I. So what will be my Ke rotational? So rotational kinetic energy is half I into L square by I square. So 1 I will get cancelled. Ke rotational is L square by 2I. Okay, Ke rotational is L square by 2I, angular momentum square by twice of moment of inertia. Also we can write that L square is equal to 2I into Ke rotational. So from here we will get that angular momentum is under the root of 2I into Ke rotational. Okay, this will be the expression for kinetic energy, various expressions for kinetic energy and angular momentum. Now next comes rolling motion. Now what is rolling motion? Till now we have studied pure rotational motion, that the body is just rotating. Okay, in the previous chapters we have studied just translational, now we have studied just rotational, but today in this topic we will be studying combination of the two, that is translational as well as rotational. Okay, so we have a body which is translating as well as rotating. Okay, so we have a body, it is moving with some velocity v forward, simultaneously rotating with angular velocity omega. Okay, it is moving as well as rotating. So the combination of pure translational and pure rotational motion is called rolling motion. Now this body is in rolling motion. Okay, this body is in rolling motion. So see, as it is moving with v velocity, every point will have v velocity in the forward direction. Okay, every point will have v velocity in the forward direction. Due to this omega angular velocity, every particle will have a tangential velocity omega r also. Okay, every particle will have tangential velocity omega r also. So we can show that this motion is a combination of two motions, one in which the body is only translating, so whole body is moving with velocity v like this. This is the pure translational motion, and other one in which it is rotating with angular velocity omega, so it will have tangential velocities omega r like this. Okay, so we can easily see that this motion is a combination of these two motions. This is pure translational part and this is pure rotational part. Okay, this is pure translational, this is pure rotational. So this motion is a combination of these two motions. Such a motion is called pure rolling motion. Okay, not pure rolling, rolling motion. Now rolling motion can be of two types: rolling with slipping and rolling without slipping. In rolling with slipping, the body is rolling as well as slipping forward. Okay, but in rolling without slipping, the body is not slipping forward. Okay, so let us see the contact point C is having two velocities. One is v forward and the other is omega r backwards. So if first case v is greater than omega r, then the contact point will have a net velocity v minus omega r in the forward direction. So this is called forward slipping. In this, the body is moving forward, rolling plus slipping in the forward direction. Okay, this is called forward slipping. Next case comes if omega r is greater than v, then the contact point will have a net velocity in the backward direction, that is omega r minus v. So this is called backward slipping. Okay, this is called backward slipping. In this, the body is rolling as well as slipping backward. Okay, rolling as well as slipping backward. Now third case, that what if v is equal to omega r? Okay, if v is equal to omega r, then the contact point will have net velocity 0. This is called pure rolling. Okay, this is called pure rolling, that the contact point is having net velocity 0. Okay, v is equal to omega r. Very important condition for pure rolling. Contact point is at rest with respect to the surface. Okay, contact point is at rest with respect to the surface or ground. Net velocity will be 0. Now what will be the velocities of the all other points in pure rolling motion? So if I have a body moving forward with v, every point will have the velocity v. Now because v is equal to omega r, so every point will have omega r like this, which is equal to v. So every point will have another v like this. Okay, so net velocity of all the points, this will be equal to 2v, this will be equal to root 2v like this. This will have net velocity 0. This will again have net velocity v is equal to root 2v. Okay, these are the net velocities of all the points in the pure rolling motion. Now what if my body is accelerating? Okay, what if my body is accelerating? Now if the body is accelerating forward with acceleration a, every point will have the acceleration a in the forward direction. Okay, also simultaneously it is rotating with angular acceleration alpha. So every point will have the tangential acceleration alpha r like this. Also every point will have a centripetal acceleration omega square r. Okay, every point will have a centripetal acceleration omega square r. Now we can define this motion also as a combination of these two motions. Okay, translation as well as rotational. Okay, we can define it as combination of two, translation plus rotation. Now draw the translational part. Every point will have the same acceleration a in the forward direction. Okay, every point of the body will be accelerating with acceleration a. Now let us draw the angular acceleration part. So rotational part, every point will have a is equal to alpha r, a tangential acceleration and a centripetal acceleration as well. Okay, so draw the centripetal accelerations, omega square r, like this. Now this is pure rotational and this is pure translational. Just see that this motion is a combination of these two motions. Now what will be the condition of pure rolling in this case? Okay, so condition for pure rolling motion in this case will be a must be equal to alpha r. Okay, condition for pure rolling becomes a is equal to alpha r. The point, contact point, cannot accelerate forward or backward with respect to the ground. Okay, this is pure rolling motion on a horizontal surface. Now let us see pure rolling motion on an incline. Suppose we have an inclined plane of inclination theta and we have a body. This body could be any body, ring, disc, anything, solid cylinder, hollow cylinder, solid cylinder, hollow sphere, solid sphere, anything. Now if m is the mass of the body, mg sine theta will act forward, so friction will be acting backward. Okay, now this is the r radius. If this body is moving down the incline with acceleration a, and due to friction, see, mg sine theta is passing through the center, it will not provide any torque. But if you see about this point, friction will provide a torque, so it is accelerating with a torque alpha. Okay, accelerating with the angular acceleration alpha. Then let us write the equations of the motion. We will get that mg sine theta minus f is equal to ma, force is equal to mass into acceleration, tau is equal to I alpha. So what is the torque? For friction is providing the torque, F into R will be the torque, m k square is my moment of inertia, k is its radius of gyration, into alpha. Okay, and for pure rolling we have the third condition, that a must be equal to alpha r. So from here alpha will be a by r. So from here friction will become mk square into a by r square. Substitute this in this equation, we will get that mg sine theta minus mk square a by r square is equal to ma. M gets cancelled, acceleration will come out to be g sine theta divided by 1 plus k square by r square. Very, very important relation, that acceleration of a body down an inclined plane. Okay, very important relation. Okay, what will be my acceleration of the body down an inclined plane? G sine theta divided by 1 plus k square by r square. Now let us calculate friction. Friction is mk square by r square into a. Substitute the value, so we will get that mk square into by r square into g sine theta divided by 1 plus k square by r square. If you solve this, okay, we will get that friction is equal to mk square into g sine theta, mk square into g sine theta divided by r square plus k square. Okay, this will be the friction. This will be the friction. Okay, now let us see time if this inclined plane is of length L. Okay, if this inclined plane is of length L, this is a constant acceleration, so we can calculate the velocity at the end of incline, velocity at the bottom of incline, velocity at the bottom of incline will be v is v square. V is equal to under root of 2a into L. Okay, to v square minus u square is equal to 2as. Okay, solve this, put the value of a, you will get it. Okay, so v will be under root of 2gl sine theta divided by 1 plus k square by r square. Okay, this will be the velocity of at the bottom of the incline, velocity at the bottom of the incline. Now next is time taken to reach the bottom of incline, time taken to reach the bottom of the incline. T will be equal to under root of 2L by A, so it will be under root of 2L into 1 plus k square by r square divided by g sine theta. Okay, this will be the time taken by the body to reach the bottom of the incline. Okay, this is all about rolling of body down in inclined plane. Now let us calculate its kinetic energy. Okay, so because the body is moving forward, total kinetic energy, okay, total kinetic energy is kinetic energy translational plus kinetic energy rotational. So kinetic energy translational will be half m v square and kinetic energy rotational will be half I omega square. So kinetic energy will be half m v square plus, we can write I as mk square, and we can write for pure rolling, because it is pure rolling, v will be equal to omega r, so omega will be v by r, so we can write it as v square by r square. Now take whatever it is common, we can see that half mv square is common, we will get 1 plus k square by r square. This is the total kinetic energy in the rolling motion. Okay, this is the total kinetic energy in the rolling motion, a very very important relation. Okay, very important relation. So this is the end of our chapter, rotational motion. I hope you liked the video and you found it helpful. For more such videos, do follow this channel. Okay, so we will be posting such content, we will be completing this whole series of ultimate recap sessions. I hope the series is very very useful to you, so keep watching it, keep rocking, keep studying. Okay, bye bye, take care.